this gold co-deposition. When we were talking about D2 formation and palladium near monovacancy the other day, palladium especially had the biggest such effect. Nickel was number 2, gold was number 3, and Let's has observed excess power in gold co-deposition without any palladium around. So the thought being is that gold is sort of like palladium, maybe not as good as palladium, but gold has the potential of being active as well. We talk about the 2-laser experiment. After seeing the single laser experiment, I went over and I took Let's out into a hallway, and when theorists interact with experimentalists, well, you know how it works. So I said, Deb, why not try a 2-laser experiment? And Deb said, why in the world would you want to try 2 lasers? And I said, well, in quantum optics, people will do 2 laser experiments because sometimes phenomena respond to peak frequency. And if you can do a 2-laser experiment, get the exp't to turn on with 2 lasers, maybe it's going to care about the difference between the 2 lasers and frequency. And if so, maybe that gives you a way to probe phonon frequency or frequencies in the vicinity of phonon frequencies. So Dennis responded, when a theorist says jump, the experiment says, well, how high? So Dennis responded immediately. So 5 years later, he did the experiment.
5 years later? That was a jump.
And it worked. So here's an example of the effect. So now excess power, 2 lasers turn on. When they turn on, in this particular case, with a frequency difference that turned out to be one of the sweet spots. And it can be seen sensibly and rationally to initialize, to turn on the excess power. And even though this is one of the best examples and cleanest to plot, having gone through all of Dennison's data, you can see this turning on effect again and again and again and again. It's generally a reproducible thing. If you got your laser tuned to the right sweet spot frequency, you put the lasers in a Dennis experiments, the exp't follows. And in this case, it goes up to a constant value, and many times in Dennis's experiments, it goes to a constant value. There's sort of an artifact here, which is connected with when the lasers turn on, there's a change in the over potential, a change in the self potential. And it takes Dennis's electronics a little bit of time to readjust, to reestablish the input power to be right, which gives a little blip. And this kind of little blip has actually been seen since 1989 in many experiments. A lot of experiments just before exp't turns on, there's a blip because the cell potential changes. So let's assemble the results from a very large number of experiments done over 2 years in Dennis's laboratory. And let's make a plot, send it in, have a reviewer throw the paper back and say, I want to see error bars. So you go back and you calculate everything. I could explain what was done, but we did fitting against a relaxation curve in the case of every single data point lot. I did it and made up all the error bars for it. And here you go. So there seems to be 3 frequencies where you get a response. And these wily experimentalists, when the theorists say, I would like you to do this experiment, what's the first thing an experimentalist says? Well, what's your prediction? What do you think is going to happen? Right? And I said, well, obviously the thing's going to respond at the phonon frequencies where the group velocity is 0. If you put your energy into the vibrational modes, you want it to stay there. And at frequencies where the group velocity is finite, then the energy will just leave when you put it there. And it's also got to go into compressional modes, because we know from the single laser experiments that if you come in with the P polarization to couple to compressional mode, you can get the exp't to turn on, but if you come in sideways, then you don't get any effect whatsoever. So we got 2 frequencies correspond to the gamma point and the L point in the phonon dispersion relation, and this point corresponds to gamma point 0 momentum there's a compressional node, and that's where you'd expect zero root velocity. At the L point, this is the other compressional node, and that's somewhere near, from the literature, near 16 terahertz. If I go back and I look. So here's 8 terahertz showing up at the gamma point. Here's basically 16 terahertz showing up for the L point operation. And of course, then people say, "Oh, okay, so that one makes sense. That one makes sense. What the heck is that?" And we don't know. One possibility is that we might have some hydrogen contamination. Now, we showed last lecture that the solubility for hydrogen is something like eight times more for deuterium. So if you have like 1% hydrogen contamination, you can get about 8% hydrogen substitution into the cathode. So if you have some hydrogen, then you get an L point response for hydrogen, which is a little bit under what it is for adenosine, so that's one possibility. Another possibility is it might be L point associated with the gold, hydrogen gold. The solubility is not very high, so that counts as stretch. Anyway, that's what we know. I guess if you like, the reason that I'm presenting this is that in Dennis's experiments, when he puts the laser on, it can simulate an excess heat event, and once stimulated, it will stay on. He found in these experiments it stayed on. So we turned the lasers off, the excess heat was unperturbed and stayed on for about 2 weeks. So the thought being is that once you established vibrational excitation in the mode, that it would draw the nuclear energy into it and sustain the mode. That's the line of thinking behind these experiments. So, if you like, as a general principle, if you want, and according to the models I'll be talking about, if you want the energy to go into vibrations, you need to establish excitation of vibrations. So what I want to argue is that the current, well, if you get deuterium fluxing through the palladium, when it goes from site to site to site, it's a very noisy thing, and that generates optical phonons as well. So the question is whether excess power would respond to deuterium flux. And one measure of deuterium flux is the electrochemical current. Namely, if you increase the current, you decrease the current, you change the loading, then the loading changes because deuterium is fluxing across the boundary. And since all the vacancies are near the surface, that's where it counts. So what was seen is that as the current increases, the excess power seems to be correlated, and higher current sort of means higher generation of optical phonons consistent with deuterium flux. So this has been seen by many people. Now, in the M4 experiment, this is going to be tough to explain, but I'll try. In this experiment, the loading was measured. And so the loading's over here, and it corresponds, I think, to this curve. So here's loading. The current is this curve, so there was a little bit of a current increase, which Mike likes to do to try to simulate an excess power event, and then it's held constant. But now the excess power, which turns on here, has got all kinds of interesting dynamics. And it's got all kinds of interesting dynamics sort of in a region where there's no change in the current, there's no substantial change in the loading. And the question is, why in the world is there excess power? So Mike and I were chewing this over, and I was trying to explain to him the ideas about, well, flux correlating to making phonons, and the phonons being what you need in order to get the excess power. So Mike said, well, let's look more closely at the loading here. And if you blow things up, what you find is that the cathode on its own is breathing. These cathodes are like really complicated and so forth. So it's breathing deuterium in, it's breathing it out, in, out, and the excess power locally seems to be correlated to this breathing effect. So what Mike did is he said, well, let's try an empirical fit where above the threshold, we're going to be parabolic with loading, linear in current density, but now let's add a flux term here. So if the loading changes, breathing in and out, that's giving rise to excess power as well. So here's some, so these guys are the measured excess power values. Using this kind of fit, here's the predicted values. Now what happens in this region where sort of nothing's going on but the breathing's happening, this new metric is seemingly doing a reasonable job of capturing the excess heat associated with the breathing. So these arguments are suggesting that the deuterium flux can stimulate excess power, sort of consistent with these ideas. That leads us to the energetics experiment. In the energetics experiment, part of this funny current profile they use to drive excess heat is causing the deuterium on purpose to flux in and out of the surface and flux a lot. And this kind of current mode is what was used to get this very large event. So as we showed the other day, input power, excess power. So we get energy gains, something in the neighborhood of 25 for this experiment and for a few others like it we observed with the energetics laboratory. Sorry.
Got it.
Okay. Finally, suppose you have flux. Can you quantify how much power is going into your phonons? And let's see. The local heating would be the current times the change in chemical potential. In essence, you can relate the local power depository and volume by this flux. So the current divided by basically the resistance that you can associate with the deuterium diffusion, which is associated with the deuterium version of Ohm's law here. So as a result, we can calculate how much power you're dissipating connected with the flux. And the thought is that power is going to the vibrations. The vibrations, once they get going, are allowing the energy to be drawn in. And that seems to be consistent with experiment. There's other experiments where electrical currents applied, which draws electrons, but the ions are charged slightly positively, and they go the other way. Fleischmann talked about this by CCF4. Celani and Preparata. Celani was the first to record experimental results, which showed that when you impose an axial current, you could actually stimulate anomalies in palladium deuterite. So people have seen charged particle or energetic particle emission at low levels, neutrons as well as excess power. Preparata did experiments. These days, Godus, associated with the Berlin, is using very short electrical pulses basically to do this kind of thing. He notices it gets excess power when he puts it in his pulses. He would tell you a very complicated mechanism by which it works, but if I stare at this, these experiments are very closely related to earlier experiments that have been done very similar, which show the same effect. SRI recently loaded targets, froze them, put them in cryogenic calorimeter, and they put current through, got excess energy. For palladium deuteride, for nickel deuteride, less so for palladium hydride, actually, which is interesting. Anyway, takeaway message. The takeaway message, we started the discussion by saying the energy is not going into energetic particles. Where is it going? And we don't have a direct measurement of where it's going, but we have a two-laser experiment in which if you stimulate an optical phonon mode where the vibrations stay localized, the gamma point and the L point, that that seems to stimulate the excess heat. When you turn the lasers off, the heat persists, and the picture that's behind here is maybe the energy is going into those modes to maintain organization of the effect and keep things going. And so that provides indirect evidence that the energy is actually going into vibrations prior to thermalization. What we need is I don't know, better experiments to focus on that, figure out clarify what it is that's going on at higher resolution. Let me pause for a moment, take away the message. Other comments or questions or thoughts?
Question. What on earth induced the people to use a laser on it?
For the first time?
Yeah.
Oh, they were doing everything. They tried RF, they tried lasers. I mean, these guys are tinkerers. Say what?
Cat's fur.
Actually, Dennis Craven's put together something called fairy dust. He had some rare earths, had some thorium, and so forth. We put it in the electrolyte, hoping it would make things work better. And in some experiments, it seemed to. Dennis puts magnets on, and he saw that the excess power is higher with magnets. So, the theorist types talk about a rational ordered universe where you have a logical reason to do everything. And so when the two laser experiments were done, Dennis had these magnets on. I said, Dennis, why do you have the magnets on? And my conclusion is a superstition. He did an experiment where he put the magnets on and it seemed to help. So he's never taken them away. I hassled him recently. He's now got data with different magnetic field strengths. There's some evidence now, rational evidence, the magnetic field increases the excess power. I don't know if Mitchell will talk about that topic or not. I would hope so.
Another one. If we just assume you can induce the reaction or the excess energy going on, did you ever try to stop it on purpose?
Of course.
And are there different methods that work better than others, and could you draw conclusions from that?
The issue of turning the reaction off is a very long history, really big topic, and we've made many attempts to learn something from turning excess power off. And if you like, one of the most significant was a failure in that regard. That was in the two laser experiments where I said, well, Dennis said, well, I got some excess power, but I want to go out and do my experiment in the next experiment. So, well, just turn off the lasers. So he turns off the laser, the excess power stays the same. So excess power's not going off. So how do I get it to shut off? So I said, Dennis, you're asking me, do you have a gun? Anyway, he didn't try that, but if you turn the current down in these experiments, then that will surely make the excess power go down. If you lower the temperature, that's expected to make the current go down. There's some evidence for that as well. Also, Dennis has some alternative evidence where he did an experiment, got two laser experiment, got excess power, and then cranked the temperature up, and then did it again, got excess power, and the power was higher level, which is now why we know something about temperature dependence excess power.
That would have been my next question. So yeah, starting it and stopping it at different temperatures, is there any indication that there is?
We don't have data for that. We have data for an experiment where a run was done at one temperature. The lasers were turned off. In this case, the excess power drifted slowly back down to the ground, which said, Dennis, you told me the excess power never went back down. All it did was stop, Dennis. And then when it was down, then he raised the temperature and tried it again, and more than doubled the excess power for the same parameters. Other questions? All right. I'm going to conclude the last part of this lecture by, I'm sure, putting absolutely everybody to sleep. So I'm going to begin the discussion of theory. So the way it's going to work is I'm going to try to get the basic notion out, plus there's a toy mathematical model that, in my view, captures the heart of what's going on in these experiments. However, as a toy mathematical model, if you try to connect that toy mathematical model with physical parameters of the system, it turns out you get no joy, which was the cause of about 10 years worth of hair falling out. I don't have much hair left because of that experience. about a year ago, a little bit more than a year ago, I made some progress on it, and I now have a physics-oriented model. And I'm going to talk about the physics-oriented stuff tomorrow. So today is initial ideas, thoughts, and the first step towards making the model that captures the effect. So the issue is excess energy in Poisson plots, but no commensurate energetic nuclear radiation. From my perspective, that's the biggie with respect to what's going on. In nuclear physics, conservation of momentum and energy dictates that your energy produced comes out as energetic particles. Here, based on experiment, that's not happening. So that's by far the biggest theoretical conundrum. No 24 MeV gamma, Q value 24 MeV, and human diffusion. So anyway, I'm trying to summarize all the things we've learned so far.
By scrubbing, you mean getting that helium out. Okay.
So, I mean, if you like, we've actually made a lot of progress. The loading requirements, the 0.85 loading requirement, 0.95 loading requirement, the co-deposition, all of this seems to be consistent with a picture of vacancy formation, D2 formation. You make helium, you try to get the helium to diffuse out, higher temperature helps. We've seen the helium, the two laser experiment indicates maybe that the energy is going into vibrations, optical phonon vibrations. So we've actually, in the course of this class so far, we've covered an insane number of topics, and we've got a picture that's beginning to emerge which seems to be connected with the experimental results. But now we've got to sit back and we've got to roll up our sleeves and we've got to think about what kind of model could possibly be consistent with that. So biggest theory problem from my perspective is connected with the absence of energetic nuclear radiation. So for example, if you start out with two V's and you've got helium-4 for ground state, you've got a 24 MeV quantum. And we're not seeing the 24 MeV quantum. We're not seeing a gamma, we're not seeing neutrons, we're not seeing anything. And from my perspective, the immediate result in terms of theory is that we're taking this big quantum and we're slicing and dicing it up into a very large number of small quanta. And the initial response from, I think there's some folks in this room that actually probably are involved with groups that do this kind of thing sort of as a standard procedure. So I kind of say, well, we can do some quanta, but you're talking about millions of quanta. I mean, a fractionation of a large quanta. And from my perspective, it's sort of been clear, like even back 20 years ago, that is what these experiments were pointed to as a theoretical problem. To make a long story short, I have models now that do that, and models which are relatively straightforward, simple models. So let me take the first few steps. We're actually familiar with building up quanta from one number of quanta to another quanta. For example, there's experiments where second harmonic generation comes. We're taking two low energy quanta, building up a higher energy quanta. I know there's some pictures. I was looking on the internet for pictures. There's pictures where you can actually see one color laser light going in, another color laser light coming in. Here's another example from a while back where 4-photon processes were used, basically nonlinear excitation directly of excited states of xenon. So the basic idea is you're taking one quantum, another, building up for a quantum. You can investigate energy levels. You're basically absorbing 4 at a time here. If you look in the literature, you can find examples. I found these papers, I think, where the 2s state of helium was probed at high resolution at 13 photon absorption. So you can find experiments where people do 10s. There's experiments that are done with Rydberg atoms and cavity where people do up to like 50 or so. There's these experiments using high harmonic generation, where an IR laser comes in and an X-ray beam comes out. And in these experiments, the interpretation is that you're taking a large number of these low energy quanta and you're combining them and making X-rays. It's got interesting time dynamics, frequency dynamics, and these pulses are very widely used for application. So this is one of the hot areas of applied physics these days. So how many quanta can you do? Well, here's some experiments where, let me see. You're starting out with, is this KRF light or something, generating 3.5 keV. You're combining over 3,000 quanta together to get X-rays in these experiments. And then if you look in the literature, you find the outer end of the numbers where people have done this the hardest to be up. I think I've seen between 6,000 and 8,000 quanta altogether. So in high harmonic generation, we have an example of a very, very extreme case of multi-quantum phenomena. The way it works is figured out by Corkum. I actually remember Corkum. We used to do X-ray lasers in years past, and he was involved in that, so the name was very familiar to me. The idea is that one part of the field, one part of the phase of the light, you get a large electric field which causes tunneling of the electron out, and the field changes. So it gets accelerated out, and it comes back, and when it comes back, it has a huge amount of energy. And it can recombine, but it's not just one electron, like every atom in the vicinity. They all do it together. And so when you get your recombination, all your dipoles are phased, and so you get phased array emission. So you get a beam coming out. So it's not a laser effect; it's an establishment of a phased array emission effect. And tomorrow, it turns out we're going to be coming back to this picture again because there's an experiment, the Carboot experiment, where collimated X-rays are coming out. And I'm going to make the argument that those collimated X-rays are the result of conversion of vibrational energy to nuclear excitation and producing phased array radiators resulting in phased array collimated emission. All right, so takeaway message is that experiment, from my point of view, is suggesting nuclear energies being fractionated and going into vibrational energy, and that an MEV quanta is being down converted into quanta that are 30 millivolts, 60 millivolts. It's a very large down conversion. It's unbelievably extreme down conversion. And we have an example of relatively extreme harmonic generation in this using Corkum's mechanism, but there's no chance that Corkum's mechanism will work in this nuclear vibrational environment. So we need a new mechanism. We need a different mechanism. Takeaway message. Comments, thoughts, questions? If you have questions, comments?
Do you have more insights into this mechanism that you'll be covering later on? Or?
Actually, we have 11 minutes left. I'm actually
I meant
covered. I'm going to have to go like twice the speed, so I'm going to talk very fast now. Not that. I want to talk a little bit about the spin-boson model. So the idea is that before coming to the physics, I want to think about the mechanism in isolation. I want to take everything associated with the physics, throw it away. I want to get a math problem that I can solve. And so because the physical system's complicated, quantum mechanics is complicated, I want to reduce everything down so I can focus on the mechanism itself. I have some few graphs on telling you what a Hamiltonian is, because usually when I give this talk, not everybody even knows what a Hamiltonian is. Do you guys remember Newton's laws? F equals ma. So here's F equals ma, force, and you can get the energy. Now, is this really bright mathematician Hamilton back in the 1830s was looking at FM equals MA problems. And he said, you know, it would be really cool to think about these problems differently, rather than thinking about them as the differential equations. Think about them in terms of basically what goes into the model. So Hamilton constructed I like to call it the Hagelsteinian. No, I mean it's a Hamiltonian. The Hamiltonian, which has got kinetic and potential terms, but if you like, but once you have the Hamiltonian, you can very simply recover your differential equations from it. So the Hamiltonian, if you like it, it's really useful. It's useful in classical physics, useful in quantum mechanics. But what it does for you is it allows you to take what is in your model and put it together. So for example, for Newton's laws, you got kinetic energy, you got potential energy. That's what's in your model. And once you know what's in your model, you turn the crank and you can get your differential equations in. So that's why when I talk about models, when other people talk about models, everything's described in terms of the Hamiltonian. So for example, Hamiltonian, classical case, kinetic energy, potential energy, quantum case, kinetic energy, potential energy. You can think about like classical and quantum systems sort of on the same footing in terms of the Hamiltonian. You can see what's in your Hamiltonian. So for this lecture, this bit of understanding is sufficient to follow everything I'm going to talk about. Namely, some mathematical techniques once you get a quantum or classical Hamiltonian to turn the crank and get answers and see what it does. But for this discussion, I want you guys to know that there is a Hamiltonian. We talk about what the models are in terms of the Hamiltonian, and that's what's important. I'm not going to require you to know how to do it in detail. So for example, suppose I have a hydrogen atom, a classical hydrogen atom. I got kinetic energy, I got potential energy. From this model, I can get classical equations of motion, I can solve it. And so what you should be able to do is you should be able to look at this and say, aha, I see kinetic energy and I see potential energy. And then if I have a quantum problem, so here's my quantum Hamiltonian, quantum kinetic energy, quantum potential energy. Same thing, I get this, that's my model, and from that model, I get hydrogen atom. Now, how I solve it and get those answers, if you're not a quantum mechanic, don't worry about it, but this can be done systematically, and there's no difficulty doing it in general. So what's more important is the notion of a Hamiltonian and what's in the model. So in the spin-boson model, the place where I'm going to start, the model has a two-level system, an oscillator, and they talk to each other. It's a two-level system, some harmonic oscillator, which corresponds to mass and spring. And these guys are going to talk to this. Now, why this? Well, atoms, nuclei, molecules, they can involve complicated physics. If only two levels are involved, you can get a much simpler mathematical problem for taking two levels. Maybe there's 3 or 4 bazillion levels. But if you focus on 2 of them, your math is simple and you can solve the problem. In terms of an oscillator, well, the vibrations in a solid, the phonons, they're basically masses and springs. And they're a simple oscillator. So oscillator stands in for the vibrations, the phonons. These two-level systems stand in for the nuclei or the atoms that are in the solid. And the only thing is now I'm going to say, all my nuclei, I'm going to say, heck with it, turn them all up. Give me 2 levels, 2 arbitrary levels. Take vibrations, lots of modes, different ways of vibrating. Let me draw all that out and say, oscillator, generic oscillator. Let me couple them together and see what can happen. Okay, so let me start with the basic toy model. Large energy difference, small energy difference. If you like, the question is can you exchange energy between the two-level system and the oscillator under conditions where this is very small, that's very big. So in a model, we can turn the crank. Here's Tanucci popularized this model. This is called the Spin-boson model. It's actually it's probably been more studied than any other super model in quantum mechanics. It's the workhorse model. for every time somebody comes up with a new mathematical technique to analyze a field theory or something, the spin-boson model is the very first one that they pound on. So two-level systems, harmonic oscillator, and coupling. And there you go. Let me show direct numerical solution, an example of a result like this. So here I'm starting with 100 two-level systems, and I'm putting them all in the, well, almost, they're in a state which isn't all of them excited, but it's close to having all of them excited. And I've got a vibrational state that's got a fair amount of excitation to start with. And I just simply solve this system by brute force. And in this particular case, there's 17 oscillator quanta going into making a two-level system quanta, and the two systems are fudged to be on resonance. And what happens is that the two-level systems go from excited to unexcited, and they go back to excited and unexcited. And the oscillator gets the energy, gives the energy back, the grade back and forth. The time scale is ridiculously slow. This takes forever and a day to happen. But mathematically, that's an example of the effect that I'm interested in. I have big quanta, I'm going to convert the energy, I'm going to fractionate it, I'm going to give it to an oscillator. And here, a model which is the best studied model in physics, the simplest model that could possibly be relevant, is doing exactly what I want it to do. Sort of. It's not doing it strong enough, but it's showing the effect qualitatively. Okay, so how does it work? I mean, if you can only exchange one quanta, a little quanta at a time, how do you get enough energy to be big? Well, the way this model works is it says exchange one, up, down, so you give one quanta at a time from the two-level system to the oscillator, brings the two-level systems down, you maintain coherence in the system while it's happening, and off you go. And that kind of picture works with analytic and numerical calculation. For the spin-boson, we derived a transformation where we were able to pull this out so we could solve for this effect very simply analytically. We even published that in JPSP, so some papers on how it works. So takeaway message is we have a model that works, one of the best studied in the literature, and we're beginning to see the effect that we're looking for. Takeaway message, questions, comments? Okay. So now the issue is it works, but it doesn't work well enough. Namely, if you take the spin-boson model, you beat on it, you say, get me as much fractionation as you can, it basically runs out of steam at about 50 quanta. You can take a big quanta, you chop it up into 50. If you try to do more than that, forget it. You get an exponentially more difficult time to do it. And I was talking about this in my quantum class one time, and first thing I have is resonance says, why is it limited? I thought, I wish I'd asked that question. It took me a couple of years to ask that question. Turns out it's less limited by destructive interference. If I set up a perturbation theory calculation, I get this way, I can go this way. And if I add up all the terms from perturbation theory, they cancel out to precision. Namely, this path contribution is a million times greater than the contribution sum of them all together. And so now I understand why. The spin-boson model can do it, but it can't do it very well because of destructive interference. If I want to make things work, I got to get rid of the destructive interference. So I tried lots of ways, and after 10 years, I found that if I add loss to the model, the loss can cause these states to decay or to be phased, which changes the destructive interference. And when I study a model that works that way, I find it works. And here's how well it works. I've analyzed it, we've published it now, we've analyzed the strong coupling on it. But basically the dynamics are harmonic in this limit. This part of the problem with the factor of 4 here basically gives you the associated sort of Rabi oscillation frequency if everything were perfectly resonance. In a strong coupling limit, if everything's strong and the energy can go, you get a factor of 1 over the number of quanta that you fractionated it to for the rate. And then you get a hindrance factor, and this hindrance factor says, well, if you're not strongly enough coupled, then it doesn't go at all. So this is an exponential thing that tells you how strong the coupling has to be. And here's the hindrance factor calculated. So at this point, I've done all kinds of numerical simulation. I've done analytic simulations. I've done approximate closed form solutions. I've done finite delta and infinite delta and limit. I've done strong coupling and infinite coupling. I've done scaling laws. I've done basically everything on this that you could sanely do. And it holds up and it works. So the argument is that we now have a model that fractionates quantum. And there are issues associated with it. It works a little bit differently than the Spin-boson model in terms of the scaling laws. In the Spin-boson model, you actually get a bigger effect the more two-level systems you have, which is huge. I'm going to stop here at the takeaway message, and we'll be picking up on this next time. But let me entertain questions. Are there thoughts or comments or questions? Okay, if no thoughts or comments or questions, next time we'll discuss this a little bit more. We'll think about the implications. And then we're going to begin connecting it with experiment. And we're going to connect it with exp't experiment. We're going to connect it with the carbon experiment.